In this video, we're going to calculate the area enclosed by a cardioid. We'll begin by slicing the shape into circular sectors to experience how, as we divide these sectors into infinitely smaller pieces, our approximation approaches the true area. We will then translate this intuition into the formula for polar area. Finally, we will set up our integral and work through it step by step to arrive at our answer. Before we start, if you don't know how polar coordinates work or you don't know how to sketch them, check out my previous videos linked in the top right corner, or you can find them in the description below. Firstly, we introduce our polar axis and begin by drawing a circle with a radius of 3. The area of the circle is pi r squared, and there are 2 pi radians in it. But what if we only considered a sector? Then we just take a fraction of the total area, proportional to the sector's angle. For a general angle theta, we can use this formula to find the sector's area. Let's sketch our cardioid. We want to find the area enclosed by it. But first, let's just consider the area in the first quadrant. We cannot just use the sector formula because the cardioid isn't a simple circular sector. But what if we approximate it using 3 smaller sectors? One corner of each sector will be touching the curve. If we sum the areas of these 3 sectors, we still underestimate the true area, leaving out this red region. What if we try larger sectors, where the other corner touches the cardioid, but now the summation overestimates the area? So let's go back to our first approach. A better solution is to use more sectors. Let's say 6 instead of 3. Our under-approximation is already much better. We can use even finer sectors for an even better fit. If we imagine the sectors having infinitesimally small angles, the approximation will become perfect. We'll call this tiny angle d theta. The area of each tiny sector is dA, and it's proportional to the infinitesimal angle. To find the total area in the first quadrant, we sum all these tiny sectors from 0 to pi by 2. The pi in the numerator and denominator cancel out, and we can also factor the constant out of the integral. This gives us the general formula for finding the area of any polar curve. To isolate just the first quadrant, we set our upper limit to 0.5 pi. We can increase this limit to capture more of the cardioid's area as we sweep through larger angles. But did you notice that the bottom half is perfectly symmetrical to the top half? Because of this, a trick is to integrate over just one half, and then double the result to find the total area. Next, we substitute our expression for r into the integral. First, we expand the squared binomial. To integrate this cosine squared term, we apply a trigonometric identity, specifically a power reduction formula. We then distribute and simplify the integrand. Now we can integrate term by term. When we evaluate at our limits of 0 and pi, we're left with approximately 3.4 pi. And there we have it, the total area of our cardioid. We now know how to integrate polar curves. If you found the video helpful, you can support my channel by liking, commenting, subscribing, and hitting the bell notification icon so you don't miss future content. Comment what topics you want me to cover next, and I'll keep that in mind.